Hi everyone, today I'm going to be recording my attempt to solve problem 1 from homework 4. So this problem is, the setup is that we have this disk of negligible mass and we've attached some point mass to it. And we're just trying to calculate the dynamics as it rolls down some ramp at an angle alpha. We do have gravity to consider, and we define this angle theta, which is kind of how many degrees the disk has rolled. I started by first defining my N1, N2 frame angled at an angle alpha, right? So if we had some other frame here that's the flat ground, then we also have some N1, N2 that is angled on top of the ramp. First, I solved for the vector from this inertial reference frame down here up into the center of the disk, RO, and I did that by just in the N1 direction, which is going down the ramp, we know that it's going to travel an arc length, so that's just going to be the radius of the disk times the angle we've traveled, and in the N2 direction, sorry, upwards, we're just moving this R distance from from the bottom of the ramp. Then to get to from the center of the disk over to our mass m, we have to take this RO vector and add the n1 and n2 components, which I found just through using trigonometry, knowing that this is r over 2 over at an angle theta, and just that ends up just giving us a sine theta and a cosine theta for the n1 and n2 components from O to m. And if you go ahead and add those together, you get the full vector of m from our inertial reference frame. Then we have to actually solve for the velocity because everything's in the inertial n1 and 2 reference frame. I don't need to use the vector differential equation. I can just go ahead and derive like we normally would. And this is probably one of our easier integrations. We just have this r theta goes into theta dot and a small dot product with this theta dot cosine, but that's pretty easy. On the n2 direction, we know that r isn't changing, so that term vanishes entirely, and we're just left with theta dot sine in that r over 2 term. Then actually taking the dot product was a little harder just because whenever there's components like this and we have to FOIL the multiplication, it can kind of get a little messy. But ultimately, you're going to end up with, this r squared theta dot squared term, and we end up being able to simplify all of it into just r squared theta dot squared 5 over 4 plus cosine theta, just using some trig identities from that sine squared and other stuff like that. Now, I also did go ahead and define some function I that was all of the components that changed with respect to theta. I did this because then it was a little easier later on when I was doing the Hamiltonian to just separate what depends on theta versus theta dot and stuff like that. So I say like t is 1/2 I of theta times theta dot squared, and then I of theta is just everything else, that mr squared times 5 over 4 plus cosine theta. Now to solve for the potential energy, I was having a bit of trouble figuring out how you solve for the potential energy, which is obviously not a vector, but we've been doing all this vector dynamics. And after doing some research, I found that the easiest way is actually to define some sort of gravity vector. So in this case, this g sine alpha and g cosine alpha represent the way that gravity is in that n1, n2 rotated frame. And then I can naturally just go ahead and take the dot product of that with the vector of Rm to find the component of the Rm vector, that distance that is occurring in the direction of gravity. So I go ahead and do that, and we do end up with kind of an ugly equation. We have this cosine alpha and we have cosine thetas there. But ultimately it is still just mgr times some trigonometric quantity that gives us that ratio. Then I need to go ahead and solve for the Lagrangian, which is our kinetic energy minus our potential. So I just go ahead and write it out in equation form because I didn't really need to rewrite the whole thing. But just 1/2 I of theta dot squared minus the potential energy function. And because everything here depends on theta, except for this theta dot squared, finding the momentum is actually very easy because that's just the partial derivative of the Lagrange with respect to theta dot, which just ends up being I of theta times theta dot. And I mean theta dot being that bigger term I defined up here. Then I did also find it useful to take this I theta dot equation and rewrite it to solve for theta dot, because then later on when we take the Hamiltonian, it makes it easier to just plug in that p theta and have that term in there. And in this case, we can see from the Lagrangian that it is time independent. There's no t anywhere. And the kinetic energy was a homogeneous quadratic. It just has this theta dot squared term. So we can use the h is equal to t plus v simplification. So I go ahead and, plug that in, and I do rewrite it here, plug that in my I of theta. And because I knew, I also plugged in theta dot, what theta dot was equal to in terms of the momentum. So we end up with this bit equation that has both our p theta and the rest of our terms. Then from the Lagrangian equations of motion, we know theta dot is equal to the partial with respect to the momentum, and the change in momentum is equal to the negative partial with respect to theta. So up here, we only have this p theta term, so that's pretty easy to solve. You just bring the 2 over, multiply it, and then we do have the theta term was a bit harder. It took some, looking into different trig identities and trying to understand how you could simplify things as much as possible. But I think this is as simplified as I could make it. And then obviously from here, we could then go on to solve for our theta double dot equation. But I think we just wanted the equations of motion for theta and p theta. So that was my attempt to solve this problem. Please let me know if you saw any issues or you have any comments or feedback. Thank you.